Hello and welcome to our webinar today, Learning to Tread Lightly in the Boreal Forest. My name is Betty Rice and I'm your moderator for today. I'm very happy to have with me Greg McDermott here at the University of Calgary and Maria Stack, who's with us from the University of Waterloo today. This webinar is part of a series presented here at the University of Calgary where we feature the research of some of our scholars and on occasion, scholars they work with at other institutions, as is the case today. The information presented is a summary of the scholars' research. We would like to ask you to submit questions throughout the webinar. We'll answer as many as possible. You'll also be able to see spots where there are resources that you can pull up, and we ask you to check those as well. We will provide a recording of today's webinar along with the slides that you'll see. If you have to log out of the program for any reason during the course of the day today, please feel free to. We will be sending you that link to the webinar and the slides. And we'd love to get your feedback through the survey that you'll see at the end of the program. I think those are the housekeeping notes we need to cover. So I'm going to do a quick introduction to our guests. Then we're going to ask you to answer a quick question. First, I'd like to introduce Greg McDermott, who's here with me in the room today. He's a professor in our Department of Geography. His research activities include the application of remote sensing and other geospatial technologies to environmental monitoring and ecology. You'll see on the page that we have his email address if you'd like to jot that down, and also his Twitter handle. Don't hesitate to get in touch with him. Joining us from the University of Waterloo today, we have Maria Stack, who is a professor in the Department of Geography and Environmental Management at the University of Waterloo. She's a Canada Research Chair in Ecosystem and Climate, and she studies the interactions between ecology, hydrology, biochemistry, and soil properties in wetland ecosystems. Again, her email is down below, as is her Twitter handle. Please don't hesitate to get in touch with her. And before we begin the presentation, we do have a slide we'd like you to answer. This is where you come in. You'll see there are some categories here, who you are in the audience. We'd just like to get an idea. So if you could just take a second or two to tick the box that most suits your category and let us know who you are, that'd be great. We are going to, as we go through the program today, I may ask a few questions as we go along as they're appropriate to the conversation, but we'll probably be holding the bulk of them towards the end of the program. We'll get to as many as we can, so please, as we go, don't hesitate to answer those questions. That'll do right now. Do we have the results of the survey? Do we take a look at those, or do we wait till... No. There we go. So you can see here, if you take a look at the slide of who is participating today, 21% in the energy sector, 10% in another related field, 24%, almost 25% who teach or study a related field, and 50% of you are interested in the topic. So thank you very much for joining us. I think without further ado, we'll get into the presentation. I believe Greg's going to kick it off.
Okay, thank you, Betty. So I thought I would start by basically describing what Maria and I are going to try and present today. At the heart of it really is a paper that Maria and I published this spring with some colleagues of ours in the journal Nature Communications, and it's entitled Petroleum Exploration Increases Methane Emissions from Northern Peatlands. So we're going to tell that story, but probably in a sort of a more accessible way, and probably go a little bit beyond what was written in the article. So first of all, I think what we want to do is talk about the boreal forest's incredible capacity to store carbon, introduce people to a land cover type that's not very well known, but it's critically important, called a peatland. The second thing we want to do is we want to talk about some of the unintended consequences of petroleum development, and maybe educate with people with the type of disturbances you find on the landscape in the boreal forest. And then we want to talk about maybe some of the things that we've learned in our research and some next steps to maybe treading more lightly in the boreal forest in the future. So before I start, I really wanted to acknowledge the partners and funders who are behind this research. First of all, there's a number of researchers from a number of different research institutions. So Maria Stack and I are here representing the University of Waterloo and the University of Calgary, but there are other researchers from the University of Alberta, from NATE, from other institutions, Environment and Climate Change Canada, Canadian Forest Service. We receive funding from a number of funding organizations, the Natural Sciences and Engineering Research Council nationally, and emissions reduction Alberta provincially. And probably most critically of all, we have a number of research partners, so Alberta Pacific Forest Industries, Cenovus, Shell, and others. I know that there are likely people out there who think, oh, well, this research is bought and paid for by industry, but that is not the case. It's actually critically important that this is a multi-stakeholder partnership we're working with here, because we're trying to understand things together and we're trying to mitigate developmental effects. So if we're not working with the people who can enact the things that we learn, I think that the research doesn't hold as much weight. So I want to describe briefly the boreal forest, because I don't want to assume too much. The boreal forest, or the taiga, as it's known internationally, is this huge circumpolar forest that actually covers much of North America and much of Europe and Asia. It's the largest terrestrial biome in the planet, and about 30% of it is here in Canada, and it covers more than half of our country. It's interesting, though, because even though it covers more than half of our country, most people don't live in the boreal forest. It's obviously more of a northern forest, and our populations are more in the south. So I want to make sure that people have a little bit of an understanding of place when we're talking about what's going on up in the boreal forest. First of all, it's an extremely interesting and dynamic place. I think it's a global treasure for a wide variety of reasons. And Canadians are the stewards, because so much of the boreal forest is here in our country. Now, when I think of the boreal forest, I'm sure this is going to be biased, but I think of wildlife, I think of water, and I think of carbon. So I'll briefly describe some of these things. First of all, wildlife. The boreal forest is a very biodiverse place. I think it's interesting because much of that biodiversity is in some of the less heralded species, sort of the mosses and the lichens and the things that aren't so furry. There are certainly other more interesting species. There's lots of Canadian icons up there, caribou, moose, and wolverines, and bears, and a tremendous number of migratory species. It's a very seasonal place, and so, for example, we have 3 to 5 billion migratory birds that use the boreal forest annually. I also think of water. The boreal forest is like really a giant sponge. It's like a massive store of fresh water that can be traced back to the Ice Age. So for example, 50% of the world's lakes are found in the boreal forest. 25% of the world's wetlands are found in the boreal forest. And this is really an important part of our story that we'll get into here in a little bit. And then the final thing that I think of that may not be so obvious to people on the call here, the boreal forest has an amazing capacity to store carbon. Now, I think when most people think of carbon and forests, they're thinking about the trees, but it's a little bit different in the boreal forest. The conditions there are such that a lot of the organic material that originates in vegetation ends up locked in the soil after it dies, particularly in wetlands. So this type of condition has been persisting on the landscape since the last ice age. So, 11,000 years ago. So we have huge stocks of soil carbon in the boreal forest. So 30% of the world's soil carbon, for example, is found in the wetlands in the boreal forest. So that's a globally significant stock. So that can be mobilized to end up in the atmosphere, as many people on the call will know that carbon is the foundation for many of our greenhouse gases. So essentially what we want to do is we want to keep that soil, or we want to keep that carbon in the soil. It's an important part of the fight against climate change. I'm going to pass it to Maria now, who's going to tell us a little bit more about wetlands.
Sure. So like Greg said, the boreal forest is this amazing storehouse of carbon. And one of the big reasons for that is that there's a lot of wetlands in the boreal forest. So in Canada's boreal, on average, wetlands cover at least 30% of Canada's boreal forest. And actually, as a country, we're home to a huge number of wetlands, about 127 million hectares in total, which is 14% of our land area. And the vast majority of those, over 90%, are actually in the boreal forest. And they're a type of wetland that we call peatlands, and we'll come back to that in a minute. But you can see there that even though on average the boreal forest is about 30% wetland, we do have these also really dense pockets. So in the Hudson Bay, James Bay lowlands, but also in northern Alberta, we have areas that are in some cases over 2/3 of the landscape is wetlands. And so that's going to become important to the story as we go along. So before I get any further, we hear this word wetland a lot, but we don't often define it. So here I just wanted to give a definition of what wetlands are from a Canadian context. So not surprisingly, wetlands are basically land that's wet. The definition is that it's land that's saturated with water long enough to promote wetland or aquatic processes. So what does that actually look like? Well, it means that we have poorly drained soils. We have hydrophytic vegetation, and that's just plants that like to live in wet conditions and that are adapted to do it. And then biological processes that are characteristic of wet environments. And this is really what Greg has already introduced. These biological processes are really the accumulation of organic material. And this happens because when the soils are really wet and saturated, there's not a lot of oxygen that can get into those soils. And so the microbial communities or the bacteria that are there just can't decompose the organic material very fast. And so it starts to accumulate, and that's what stores the carbon. And we'll come back to that in a couple of slides. So we have a lot of words that we use for wetlands, things like marsh, swamp, slough if you're in the prairies, ponds, fens, bog, and muskeg. And muskeg is a common term that we use in the boreal forest. So, sorry, just before I move on, I wanted to say that when we do talk about wetlands and when we imagine what they look like, we often think of something that's in this image here. A really wet situation, lots of water on the surface, and plants that maybe are sort of sedgy or grassy looking, like we often picture a marsh. And some of our boreal wetlands are like this, but the vast majority of wetlands in the boreal forest, particularly in the western boreal forest, might look something like this. We might think of this as a forest, and it is a forest, but it's actually a forested wetland. And so the soils there, if you were to get out and walk around, are very soggy. You'd definitely be getting your shoes or your boots wet. The water table, which is just where the standing water would be, is right close to the surface, and there's these huge stalks of carbon in the soil. And what that carbon looks like in the soil, or what we call these soils, is peat. And peat is just partially decomposed plant remains. And because plant remains are about 50% carbon, this is the reason that we have all of this carbon stored in the boreal forest. It's sitting there stuck in this peat that hasn't been able to decompose because of very low oxygen conditions. So in Canada, we estimate that our peatlands are storing about 150 to 160 billion tons of carbon. That's a pretty big number, but it might not mean too much to a lot of people listening today, but it's equivalent to about 20% of the carbon that's currently in the atmosphere. So if this carbon is to be mobilized into the atmosphere, this could create a huge feedback to climate change. So what's actually happening is that we have we're just going to take a minute here to sort of talk a little bit about the wetland carbon cycle and how does this carbon actually get into there and stored in the soil. And this is important because in wetlands, it's actually a little bit more complicated than just pulling the carbon out and storing it in the soil. So we do have the plants that are there and they're photosynthesizing. So they're pulling carbon dioxide out of the atmosphere to build their plant biomass. And like we said, when they die, they'll fall into the soil and they'll decompose very slowly. So a little bit of carbon dioxide is released, but the balance between those two is overall a net uptake of carbon into the soil, like we've said. And so we call this a carbon sink. That carbon is coming in and it's being stored in those soils. But the other thing that happens, because we have those really low oxygen conditions, is that decomposition happens very slowly. And this can produce other types of molecules. And the one that we're going to be interested in, we're going to talk a lot about today, is methane. Probably some of the viewers have heard about methane because it's an important greenhouse gas. And wetlands are actually one of the biggest natural sources of methane. So we want to understand how much of that methane is moving out into the atmosphere, potentially warming up the atmosphere, and balance that off with how much carbon is coming into the system as carbon dioxide. So that would actually be cooling the atmosphere a little bit.
So Maria, you've explained how the soil retains the carbon because of the density of what's being compacted there. We have a question here about what releases or what liberates the carbon from soil? What sort of activity causes that carbon to come out?
Right. So because, at least in wetlands, one of the really critical things is that they stay wet. And that's really, those wet conditions are what's really slowing down decomposition. Things that maybe dry them out is a good way to liberate a lot of that carbon. So if we were to drain the system, now you'd start to be able to decompose that organic material a little bit faster. Also, in this case, when we're talking about, for example, methane emissions, those are really linked to wet conditions. So when we have those low oxygen conditions, we can produce methane. So if we were to make the system a lot wetter, or maybe even flood it, we might be able to shift the balance towards more methane emissions as carbon. So when we think about a peatland in its natural condition, we know that that bit of methane that's being released is more than balanced by the carbon dioxide that's coming in. And in the end, peatlands in their natural state are net coolers of the atmosphere because they're taking up that carbon and storing it in the soil. But one of the things that we're interested in is what happens when these systems start to become disturbed. And I'm going to throw it back over to Greg to talk a little bit about some of the disturbances in the boreal forest.
Okay. So I think that at least me, before I started doing research in the boreal forest, not living in the boreal forest, my perception is that it is a big, giant wilderness with no people, no activities, just moose and bears. But the truth is that there's a lot of activity in the boreal forest. So in this map, for example, you can see that 65% of Canada's boreal forest are managed for one thing or another. So there's a lot of activity out there. There's forestry, there's mining, there's agriculture, there's petroleum, there's recreation. There's lots of things happening in this forest. So because of that, we have some disturbances. So I'm going to use the term anthropogenic footprint, even though I'm not wild about it. It'll work for our purposes here. This is the visible evidence of development in the boreal forest. So you can look at a map like this, which is produced in this case by the Boreal Science Organization, and we can see that there's actually a lot of footprint in the boreal forest. So, agricultural fields and roads and forest harvest areas and mines. So in reality, a lot of this landscape is not pristine in the traditional sense. There's been development and there's been activities. And like Maria said, what we're interested in is what is the impacts of this development. So I'm going to zoom in a little bit from the entire boreal forest to the Alberta context. And rather than look at all the different types of footprint, I want to talk about petroleum and petroleum development. So I'm guessing that a lot of listeners here are aware that Alberta is home to a tremendous wealth of petroleum products. The Western Sedimentary Basin underlies much of our province, and there's just a lot of oil and gas deposits here. Probably the most famous of which is the oil sands deposit. The oil sands deposit, I think, is misunderstood by a lot of people in the general public. When people think of the oil sands deposit, they think of the mines, they think of the surface mines. But the truth is that the oil sands are actually found across three pretty large areas. So the Peace River oil sands in the west, the Athabasca oil sands around Fort McMurray, and then the Cold Lake oil sands a little bit further south. And so these are very large areas. Together, they cover an area of more than 140,000 square kilometers. That's larger than the state of Florida. And the interesting thing about this is that the vast majority of this deposit is deep underground. So it's too deep for surface mining. So 97% of the oil sands deposit is too deep for mining. So when you think about development of this resource, it's not really so much the mines that are the most common development. It's something else. It's this in situ development where we need to actually drill down underground in order to reach the deposit. So when you encounter some of these disturbances on the landscape, they look very different depending on where you are. So if you're near Fort McMurray in the Athabasca River, where the deposit is on the surface or very close to the surface, then you're just going to see the big mines. If you're elsewhere in the oil sands area, you're going to see in situ development, and the landscape looks very different. At first glance, it looks a lot cleaner, actually, because instead of big open pit mines, we have well pads with equipment on them. They're injecting steam into the ground. The deposit is still bitumen. It's still a really viscous deposit, and so it needs to be immobilized through steam-assisted gravity. So there's drilling going on, there's directional drilling going on. So the footprint is more localized, I would say, but it actually covers a much larger area for a variety of reasons. So it's less intensive, but covers a much larger area. So the oil sands landscape, if you were to, look at the landscape in Alberta's boreal forest from the sky or in Google Earth, for example, in some of these, deeper parts of the deposit, you would see something that looks something like this in many places. I see a lot of roads where people are, moving trucks and equipment around. I see well sites where people are doing drilling to find the deposit or to the extract of the deposit. Some of these have been reclaimed. There were just exploration well pads that have been used and then reclaimed. And then I see seismic lines. So seismic lines is something that we'll talk about more carefully here, but that dense network of really light lines you can see in the map here, those are seismic lines. So a seismic line is a feature that I'm guessing that most people who are not in the petroleum industry are not particularly familiar with. So a seismic line is basically a petroleum exploration corridor. So I've already described that in much of the oil sands region, the deposit is deep underground, so we need to find it. So we need to conduct seismic surveys. So we need to deploy equipment on the landscape that allows us to search underground for this deposit. So that's what a seismic line is. It's a linear clearing from 2 to 10 meters wide that's cut through the forest to allow access to the landscape from equipment so that we can do this exploration. People have been cutting seismic lines in Alberta for a long time, since the 1940s or 50s. Back in the early days, the seismic lines were cut with very heavy equipment, so bulldozers, for example. So this is a conventional seismic line on the right here, which is an 8 to 10 meter wide corridor that's very noticeable on the landscape. As time has gone by and as our technology has improved, we've begun to cut less obvious lines in the forest. So the one on the left is what's called a low impact seismic lines, which is the kind of line that's been cut since about the mid 1990s. So these are more like 2 to 5 meters wide, and they're cut by mulchers or even in some cases by hand. Still, if you look at the landscape from the right perspective, you'll see that in many places there are a lot of lines on the landscape. In some cases, you can see places where we have both the conventional lines, which are spaced perhaps 300 to 500 meters apart for 2D seismic surveys, and then we've got these narrower low impact lines, which are smaller, but what you find is that they're often placed in a much higher density. Because we're doing 3D seismic surveys, so we need more access to the landscape. In some cases, this density can exceed 10 kilometers of line per square kilometers of forest. So they're spaced less than 100 meters apart in some cases. And there's a lot of seismic lines in the province. The Alberta Biodiversity Monitoring Institute is an organization in the province that does a variety of good things, including mapping human footprint. So, for example, here we've got a map being shown of the location of the known seismic lines in the province produced by the ABMI. And like I said, there's a lot. The ABMI has documented more than 1.8 million kilometers of seismic lines in the province. Again, that's a big number. It may not mean much, but that's enough to circle the planet 45 times.
Now, I'm curious, we're looking at the Alberta map.
Yeah.
What do we know about Saskatchewan, British Columbia, Russia? Do we know what's happening in those parts of the world? Is there monitoring like this?
Monitoring, I can't speak too much about. There's certainly seismic lines. There's monitoring going on everywhere, I'm sure. The issue with monitoring these particular features is that the large lines are relatively easy to map. So you can map them from satellite imagery, for example, if they're 10 meters wide. Even actually those are difficult, but still, there's ways of doing that. If you want to map all the lines, that takes a lot more effort. So we're actually very fortunate in the province to have an organization like ABMI who's doing this work. I don't believe that I don't think there's an equivalent to ABMI in Russia, for example, or Europe. I'm not positive about that, though. There are certainly lines in other places. You'll find lines everywhere you find deep petroleum deposits and forests. So we're talking about Alberta here, but there's certainly lines in British Columbia, in the Northwest Territories, and Saskatchewan. Anywhere there's deep deposits that need to be found before they're accessed. There needs to be equipment deployed, then we need access. We need lines. Okay, so I said before that part of our story, or maybe the heart of our story, is the unintended consequences of petroleum development. I'm quite sure that when these lines were originally cut, it was sort of thought, it's the forest, there's not many people up here, we're going to cut them, and then in a few years they'll just fill in and they'll be gone. They were never intended to be permanent features. What we've learned, though, is that that's not really the case. So, for example, Phil Lee and Stan Booten did a study a few years ago looking at how these seismic lines recover over time. And what they found is that after 35 years, less than 10% of the conventional seismic lines had recovered to greater than 50% woody vegetation. So yes, there might be vegetation on there, but it looks very different than the surrounding forest. And it's much worse in wetlands. So none of the seismic lines they looked at in wetlands had recovered to that same level at all. So no woody vegetation on the seismic lines. So it takes decades for seismic lines to recover. And this is made even worse in cases where seismic lines, once cut, start to be used by people in their vehicles or by animals that use them. So once the lines are on the landscape, what we're finding is that they're not too quick to disappear, which is, I think, an unintended thing. And these lines have a lot of impact. As I've already described, there's a lot of lines in our forests, and they have a lot of effects. Probably the most well-known of the effects are those that are ecological, related to wildlife. Woodland caribou, for example. Seismic lines are probably most notorious for contributing to the decline of woodland caribou, which are doing poorly across the boreal. But it's actually far more than just caribou. Seismic lines have been found in the literature to affect everything from butterflies to grizzly bears. This article I'm showing here in the slide is a recent work by Jason Fisher and Cole Burton. And what they found is that in this sort of oil sands landscape, like I showed you in some of the previous slides, it's shifted the entire composition of mammalian communities. So there's like winners that are doing better because of seismic lines than other disturbances like wolves and coyotes and deer. And then there are losers. There are species that are doing worse, like caribou and fox. So it has a big effect. What's less, I think, well known about the effects of seismic lines is what's happening with the soil and carbon and how those dynamics have been impacted by this development. Maria, I think we're back to you.
Sure, yeah. So this was really what Greg and myself and some of our colleagues and graduate students started chatting about as we were working in the region. It's pretty hard to work in the boreal forest, particularly in Alberta, and not come across a lot of seismic lines just because they're so dense. And so we were spending a lot of time actually just trying to map the surface of one of our peatland study sites. This was a project we were working on together, and Greg's group had collected a lot of aerial photography using drones so that we could map and create a detailed map of the surface to try to understand how this peatland was working. And in doing that, we had to walk around the site a lot to do some surveying, and we started seeing all these seismic lines on the landscape. And one of the things that we noticed was that these lines were really starting to be depressions in the landscape, that they were lower in elevation. This is probably because that heavy equipment has compacted that peat soil, which is actually quite compressible. And it might also be that even some of the surface soil has been scraped away during the construction of the lines. But because we had this data, we could create a detailed elevation map. And what became very obvious was that you could actually see, if you look at the bottom of this image here, that's the elevation map there, that these lines were depressions in the landscape. And because these wetlands are really wet, the water is quite close to the surface. So as soon as you start to depress that landscape, you bring the water even closer to the surface. It's not that the water has moved up, but the surface has moved down. And so that depression of the surface is making these peatlands wetter. That probably has big implications for the trees, and maybe probably one of the big reasons that the trees don't grow back, in that even though these are wetland trees, they don't love to be in really like a puddle. They don't want to grow in this really, really wet condition. But one of the things that I really am interested in is the carbon cycling, which we talked about before. So we started to ask ourselves, well, what do these changes maybe do to the way that the carbon is being stored and cycled in these ecosystems? So we know that the trees have been cleared away, and as Greg mentioned, they take a very long time to grow back. So this means that you get more sunshine falling on the surface. And then we also know that you have compacted that surface and made it wetter. So those two things together, more solar radiation and wetter conditions, tend to lead to warmer soils as well on those lines. So now we know that we have wetter situation, we have a warmer situation, and that removal of the trees often also changes the types of plants that grow there. So instead of having maybe a predominance of mosses that like sort of drier conditions and shady conditions, we can start to get a lot of grasses and other sort of leafy plants that maybe wouldn't have grown in the forest before. And those produce a type of litter when they die that's a lot easier to break down than some of those mosses were. And so on the slide here, you see labile carbon. And all that really means is carbon that's really much easier for the microbial community to break down. We kind of think of it as like the candy of the litter, right? The microbes can use it really easily. So in this case, we're interested in what might be happening to the methane emissions, that important greenhouse gas that comes from peatlands. So when you put all those changes together, the easier to break down litter, the wetter conditions, which leads to lots of methane production, and the warmer soils, we built this conceptual model that leads us to conclude that we should see more methane emissions on these lines. But we didn't know, or we wanted to try to figure out, by how much might this change? So we know already, this is fairly well established in the literature, that wetter peatlands release more methane, basically because of all the things we've already spoken about. So what we did was we went into the literature for anyone that had measured methane emissions previously in Western Canadian peatlands, and we pulled that data together and we related then the methane that was being released from those sites to the water table position, or basically how wet they are. And we did that for the three main peatland types that we have in the province: bogs and fens and swamps. What that allowed us to do was then to say, okay, for an average bog, this is the methane emissions that we would expect to see from that site. So basically just taking the average water table of all the sites that we found and calculating the average emissions. Now we know something about how much wetter those seismic lines get, so we're able to predict how much that methane flux might increase once we've compressed that surface and made it that little bit wetter.
We did have a question come in, and I think you answered this. It's two questions, actually. Okay. I think you just answered the second part, which was how is methane affected by solar radiation? I think you just explained that, particularly in terms of sort of the increase in solar that we're seeing in these cut lines, unless I'm getting that wrong. And the second question was about local methane emissions. How does it affect the local temperature? Are we looking at this as a broader picture, or are we looking at specifically in that area where we're seeing the lines? Are we looking at two different things there?
Okay, so in terms of, so to clarify, in terms of solar radiation, it's sort of having a knock-on effect of warming up the soil and changing the plant communities. And
Right.
those two things together are helping to enhance the methane emissions. In terms of the methane emissions, I think the question is related to whether enhancing methane emissions could then increase the local temperature as a greenhouse gas. Not really. We're talking about fairly low rates at any given time of methane release, but it's more sort of what that might mean from a whole landscape perspective of creating now another source of greenhouse gases that we, as Greg said, that's really an unintended consequence of this petroleum exploration on the landscape. And that's a really good segue into the next slide, actually, which is once we started thinking about what might happen really locally on the lines, we wanted to determine what this might mean for the whole province's peatland methane emissions. And I think Greg's going to speak to that a bit.
Okay, so hopefully now we've established that we've got a lot of peatlands in Alberta, we've got a lot of seismic lines in Alberta, and we've got this concept for what might happen to peatland if it's disturbed by a seismic line. So all peatlands produce methane, but when we disturb it and we lower the surface a little bit, then it's going to produce a little bit more methane. So we wanted to know how much more methane are we talking about here? So no one's ever actually done the analysis of like, can we just spatially look at all the peatlands in the province, spatially look at all the seismic lines in the province and see how they coincide? So that's what we did. We used publicly available data. So we used, for example, the Alberta Environment and Parks merged wetland inventory, which is the map on the left, which shows where all the different types of wetlands are. When we use the Alberta Biodiversity Monitoring Institute's human footprint inventory. And we did some relatively simple analysis. So this map, the two little inset maps, the one at the top shows the spatial distribution of seismic lines in the province, which I'm portraying here in terms of density. The little map on the bottom shows the spatial distribution of peatlands in the province. And the big map shows where the two coincide. So the hot colors are where we have high densities of seismic lines and high proportions of peatlands. And what we did then is some calculations based on the relationships that Maria described earlier. So there are over 345,000 kilometers of seismic lines crossing peatlands in Alberta, these bogs, fens, and swamps that we discussed. That's a total area disturbed of more than 1,900 square kilometers. Based on this calculation, we're estimating that between 4.5 and 5.1 kilotons of methane are being released because of this activity per year. And again, that number may be difficult to digest, but that's basically the global warming potential or the carbon dioxide potential of 27,000 passenger vehicles being driven by 1 year. And the thing we really want to emphasize is that these are undocumented methane emissions. So Canada has some national reporting obligations, and we do report what we predict to be produced by industrial disturbance, but this is undocumented because we didn't know about it. So, for example, in the category of land use change and forestry, we would have to increase our national estimates by about 8% if we included these undocumented emissions. I also think that our estimates are conservative, unfortunately. And the reason is because, well, there's a couple of reasons. Maybe the biggest reason, though, is because we don't know where all the seismic lines are. As we've described, some seismic lines are relatively big and easy to map, and some of them are small and difficult to map. Those seismic lines that Maria described earlier were the low-impact seismic lines. So even the little ones that are cut by light machinery, they still depress the surface. They still produce the wetter conditions. And even though you can't see them so easily, they still are contributing to this unintended consequence. So we wanted to sort of get an idea of how many seismic lines are we missing in these publicly available data sets. So what we did is we looked at a 10,000 square kilometer portion of the lower Athabasca near the town of Conklin, and we used a much higher resolution data set. So this is where we have more faith that all of the seismic lines are mapped, even the narrow, low impact ones that might not be available in the public database. So in the big map here, you can see the black lines are the publicly available seismic lines. So that's from the ABMI publicly available database. And the red lines are from this higher resolution, more enhanced mapping effort. And so you can see that there's a lot of red lines that are not coinciding with black lines. They're not in the public database. And what we found is that in this landscape, at least 70% of the low impact lines were missing from the public database. So I think that we're underestimating by a fair amount the volume or the area of wetlands that are being disturbed.
I've got a question here, and I'm not exactly sure of what it pertains to, but it's the figure 8% just for Alberta. Is that?
No, if we took Alberta's, if we took, we're only estimating boosted methane emissions in Alberta.
Right.
But that amount would increase Canada's national
The
reporting.
entire of Canada for 8%.
Not for all of methane, but only in the category of land use change, and forestry.
Okay.
So I don't want to misrepresent anything. It's just a single category of methane.
Okay.
But it's the national number that would have to increase by about 8% if these emissions were included.
Got it. Thank you for that clarification.
Okay, Maria.
Right. So we wanted to take a little bit of time at the end, now that we've talked about what some of those unintended consequences are, we're also working a lot on how can we mitigate some of those disturbances as they're ongoing, but also how could we restore and reclaim to sort of prevent these from just continuing to be sort of disturbed sites moving forward. And this is really the sort of the broader theme of the webinar today is how can we tread more lightly in the boreal forest? So I think the very first thing we need to do, and this has been, I think, apparent to us in doing this work, is that there's probably a lot of unintended impacts that exist out there that we just haven't really quantified yet. It's because there's a lot of different uses going on in the boreal forest right now, and it's a big place. So we need to work to now better quantify the full extent of these impacts. So even in this work that Greg and I have done here, it's based a lot on the theory that we know about what should happen without a lot of direct on-the-ground measurements of whether we actually see these boosted emissions or whether we might be underestimating or overestimating what they are. So this is some of the work of one of my PhD students, Percy Corsaw, right now, is to actually get out there on the ground across a whole series of these seismic lines and actually measure what's happening, not only to the methane emissions, but also the plant productivity and how much carbon that they're still storing in the soils, so that we can have, if we don't measure it and we don't know what is there, it's pretty hard to mitigate it or to restore it. So we're trying to get a better handle on, what effects are actually happening. I think the second thing, though, is that we need to start working towards developing best management practices, but also effective restoration methods. And this is particularly important for wetlands, where these wouldn't have been locations traditionally where there would have been a lot of forestry going on. So we don't really have good methods in a lot of cases for getting trees to grow back on these sites or for restoring them back into functioning ecosystems. And we really believe that this is going to require an active collaboration between academics, but more importantly, with the other stakeholders who are actually going to put these actions into place on the ground. So that includes our industry partners. It includes governments that are often making the, for example, restoration reclamation requirements, so that we're sure we're developing techniques that are going to meet those and informing what those requirements should be. And then, of course, non-governmental organizations as well. And I have a long history of this through the Peatland Ecology Research Group that's worked with the horticultural peat industry in Canada. So we've been talking a lot about petroleum disturbance so far today, but one of the other uses we have in Canada for peatlands is actually to produce horticultural peat or growing media. So if you go out to your garden center, if you're a gardener and you're buying a potting soil that has some peat in it, it's come from probably one of these boreal peatlands that we're talking about today. And when we're done with that activity, we often have just a bare peat field. And so collaborating with that industry over 25 years has allowed us to develop a method that is really effective at returning peatland vegetation. And that's what you see in the bottom here. So now we actually have some lessons we can take from that into looking at these other types of disturbances on the landscape, but also a really good model of that industry academic collaboration. And so I just want to do a really quick case study as to how we might put this in practice for petroleum disturbance. And one of those other disturbances that is widespread in this in situ type of development are well pads. I think Greg had a nice image earlier that showed those sort of squares on the landscape where they're drilling. And it involves putting a thick layer of mineral soil fill, or sort of gravel and sand and silt, on top of the peatland so that they can actually put their drilling equipment there. So when you're done with that drilling, you no longer have a peatland, you have this sort of a gravel parking lot that needs to be removed or reclaimed. So we've been working with some partners, including Shell Canada and Canadian Natural Resources Limited, on some projects on how we could reclaim that. And one method that we've tried is what's called burial under peat, where some of that surface mineral material is removed. The peat underneath is then excavated to sort of decompact it. You can actually bury some of that mineral soil fill under the peat and then place the peat back down, so you have a nice sort of soil surface that would be very similar to an undisturbed peatland. And using what we've learned with our other restoration trials, we reintroduce the plants, and you go from something then that looks like the upper photo here, which is that bare peat surface that we created after removing the pad, to 1 year later having a good cover of wetland plants on the surface. And then if you go back several years later, you can actually start to see some of those woody shrubs and trees coming back, and a lot of the mosses that are really characteristic of the peatland environment. So this is one example of how we can start to work with industry to develop some restoration methods.
So Maria, would these be the same plants that we would have seen in this area previous to the original excavation?
Yes. So often in the first year, it might be more of sort of early successional plants, a lot more of sort of very leafy species. And then often within, after you sort of start to see 3 to 5 years, we can start to see a lot of the mosses and the more woody plants that take a little longer to establish starting to come back into the system. This is also ongoing research, so it's something that, when you're in early days, it's hard to know, what's the trajectory of this site over time. But that's obviously a really important question for industry, as well as when we're talking about policy, as to how long do you need to monitor these sites before you know they're on a good trajectory.
Mm-hmm.
And just to come back to the seismic lines that we've been talking about, of course, there's also a lot of work now because we're starting to understand better what some of the impacts are on how can we reclaim these sites. And the focus is really on getting those trees to grow back, because that's the really visible disturbance, and that's obviously very critical to the habitat use of these lines. And so there's what the main method so far has been mounding. It really comes from forestry to create these higher locations on these, particularly on the wetland lines, to create dry enough conditions for trees to root. And so we're really interested in that. But maybe the difference here in these wetland systems is that the soil is peat, and it's not the mineral soils that we're often used to using in forestry. And so we're also working on some trials to see what might happen if we keep those mounds a little bit more intact, so we get a lot of the soil structure that's been built by those mosses, and whether that may lead to better or worse outcomes than some of the more traditional mounding. And we're really excited that our industry partners are willing to compare these different methods to really work towards getting the best and most effective restoration technique that's really going to return functional ecosystems.
So is this a question of mitigating what's already there, or moving into the future to look at what can be done as exploration continues?
Right. So I think there's a bit of both. So definitely this that I'm talking about here is restoring the sites that we already have in place, trying to stop them, to return their function back to more as what it would have been before they were disturbed. And clearly there's a large need for that, just given the sheer number of lines that are on the landscape. But there's also a lot of active work on how can we mitigate the disturbance as we're exploring. So how can we make these low impact lines even more low impact? How how can we do geologic exploration without the need for seismic lines? And I know there's a few companies in the province that have developed technology to make that possible as well.
And is there a commitment from some of your partners? Because obviously this comes with some sort of a cost. There's work that needs to be done. Is there commitment from the partners to move forward in this way?
Yes.
Yeah, I think
we've got a large number of industry partners, and we're proud of these companies, which are, many of the leading companies in the province that do take this seriously.
So just to wrap up, and I know that there'll probably be a few more questions here, but we, just to sort of say, well, what are some of the take-home messages from some of the things we've talked about today? Well, I think we've shown that the anthropogenic disturbance is fairly widespread in the boreal forest. And this extends beyond some of the maybe traditional disturbances we might think of, like mines and forestry, to these other types of widespread disturbances, such as seismic lines or well pads, for example. I think we're doing a better job all the time of mapping the full extent of the disturbance, but we're still uncovering what this means for the region's function, as we have these disturbances locally, but also the combined cumulative effect of those disturbances across the landscape. So when we think about then how can we remove some of that footprint or tread more lightly, it's going to require to continue that work of quantifying what the effects are that exist, and then really working in these multi-stakeholder partnerships to develop the best strategies that can mitigate the impacts, but also to develop restoration techniques to try to put back the function in places that have already been disturbed. And again, because we just want to sort of put up again to acknowledge all of our partners that we've had working on this work. And I think we have some time for questions probably, Betty.
That's great. Thank you. I actually have one that I'd like to ask, and it's at the beginning, Greg mentioned that some of these lines that we're talking about are 40, 50 years old, that this type of exploration has been going on for some time. Is there someone's responsibility to take care of some of these older lines? I mean, some companies no longer exist. We might not even know whose lines they are. Where does that fall? Where does the responsibility for cleanup and mitigation of those lines fall?
I don't know that I can answer that authoritatively. My understanding is that no one is legally obligated to reclaim or restore seismic lines. So the restoration activities that are going on are because these leading companies care enough to make it part of their business. Mm-hmm. But unlike well pads, for example, which it's legislated that they need to be reclaimed, it's not the same thing for seismic lines. So like Maria said, this is sort of a two-pronged issue, part of which is doing a better job in the present and in the future in not treading more lightly. But the other problem is that we have these 1.8 million kilometers of lines, many of which are legacy lines, which are very old, which there's no obligation for anyone to fix those.
Well, and as you say, some of them have become transportation corridors for animals, for humans. They're actually being used in a regular sort of way. And so that's not the sort of thing that, even if you were to try to bring them back to where they were, they've become passage routes.
Right. So there needs to be some sort of lever to encourage that restoration. And so one of the big levers that's happening now in the province is caribou. So caribou are, federally threatened, federally listed species, and provincially for that matter. And so that means that there's now, guidelines under the Species at Risk Act. So for example, we need to identify core caribou habitat and then do things that keep disturbances under a certain threshold. So many of the operators in Alberta are restoring seismic lines for the purpose of caribou. And I think that that's great. I will point out that how a seismic line is restored for the purpose of caribou might be different than for another purpose. So one of the things we're interested in are some of these applications or some of the things that we're doing on seismic lines to help caribou, do they also help, for example, methane? So there's lots of work to do on that respect.
Okay. You've mentioned quite a bit about the boreal forest. Does that involve any Arctic or subarctic tundra? Is that part of the forest? And is that any different than the wetlands we've been talking about?
Well, the boreal forest sort of blends into the tundra as you go further north. There are peatlands in the tundra. I think we start to run into additional complications the further north we go. This is more in Maria's area, but permafrost also complicates things too as we get further north.
Sure.
Yeah.
Yeah. So there are definitely the boreal forest, even as it stretches up into the Northwest Territories and the Yukon, starts to have sporadic and discontinuous permafrost, and definitely some research on lines, these seismic lines, when they're in permafrost regions, could have even maybe more intense hydrologic impacts, because there's some evidence to suggest it starts to thaw the permafrost more rapidly. So I think it's all sort of ongoing things that we're starting to discover as we move forward. And of course, the knock-on effect of those industrial disturbances with ongoing climate change makes things even more complicated.
We have a question here. Somebody wants to know, has anyone done an estimate for the total impact of these disturbances across Canada? How much of an increase in carbon emissions accounting would these impacts across Canada be? But I think you answered that question. But is there anything else being done outside of Alberta, I guess, is the basic question here.
So, yeah, maybe I can take that. I mean, when Greg answered earlier about just do we know where the lines are, that's one of the biggest things that's really hindering this as a cross-Canada study. There's definitely been some work by Natural Resources Canada to try to map all the disturbance in the boreal, but it's really had to depend on satellite imagery, and that doesn't do a great job of capturing these lines. And in other provinces and territories, the records of just where the lines are is not as strong as what we have in Alberta. This is why we started with the study in Alberta. But this is an active area that Environment Canada is trying to work towards, because they recognize they do need to report on these emissions. They just also need to come up with a robust and defensible way to actually do that accounting.
Is there any discussion about legislation for the restoration of these lines? Is anybody talking about becoming a legislation that they be mitigated?
Not that I'm aware of outside of levers like the Species at Risk Act.
I was going to say, I have spoken to a few people in the Alberta Energy Regulator, and they're interested with what we're doing, because the assumption has always been that these lines will recover on their own. But I think, with the legacy of some of these lines, it will be very difficult to legislate whose responsibility will that be.
Sure.
They are using some other mechanisms in that there's other ways to fund environment improvements. For example, Environment Damages Fund, that they are using to do some small restoration projects where they can.
I'm going to ask one last question because we're almost out of time, and I'm curious, what's next for you two? What are you going to be doing now?
Lots of things, but
continuing the work. So, I mean, the slide that Maria finished on here talks about our team, many of which are continuing to move forward. There's an umbrella organization that several of us are working under called BERA, the Boreal Ecosystem Recovery and Assessment Project, which is sort of where some of these lines of research are starting to, coalesce in terms of Maria Strack and I's labs and some of our colleagues at the University of Alberta. So we're continuing to do this work. I guess if I was smarter, I would have made a slide to point people to.
Can you say the name of that organization once more? And is there a place where people can?
Sure. So BERA, the Boreal Ecosystem Recovery and Assessment Project.
And if they Google that, they can probably find it and get some more information about that.
Yes.
Okay. All right. We are out of time. I can't thank everybody enough for joining us, particularly Maria and Greg. Thank you so much for your expertise. Really appreciate it. As we said, the slides and the recording will follow. We should be sending that out to you tomorrow. So thank you very much for participating. There is a survey that you can see. Please take a few minutes to fill that out. It won't take much of your time. And do sign up for other webinars, download our ebooks, watch videos on the outcomes of our scholars' research. You can find that all at ucalgary.ca/explore. for. We do have a couple of webinars coming up. October 8th, we're going to have a voters boot camp because we hear there's an election coming. And October 16th, we're going to have a program on engineering a cleaner, safer energy future. If you've got some ideas you'd like to share with us, don't hesitate to email those ideas to us. The email address is exploreucalgary@ucalgary.ca. And once again, thank you very much to Maria and to Greg for taking your time today, sharing your expertise. We really appreciate it.
Oh, thanks for having us.
Thank you.
Thanks very much.
Thank you.